Welcome to our lecture on reducibility tests in ring theory. Today we are going to explore a fascinating question. How do we know if a polynomial can be broken down into simpler pieces or if it is already in its most fundamental form? This concept is the algebraic equivalent of finding prime numbers, and it is absolutely essential for everything from solving complex equations to securing modern digital communications. Let us dive in. To understand reducibility, imagine you are playing with interlocking toy bricks. Some structures can easily be snapped apart into smaller pieces. In algebra, polynomials act exactly like these structures. Factoring a polynomial means breaking it apart into smaller, simpler polynomial pieces that multiply together to form the original. If a polynomial can be broken down this way, we call it reducible. But if it is like a single solid brick that absolutely cannot be factored into smaller valid pieces, we call it irreducible. Reducibility tests are our diagnostic tools to figure this out without endless guessing. Now that we understand what reducibility is, we must introduce a crucial rule. Reducibility depends entirely on the field you are allowed to use. A field is simply a number system where you can add, subtract, multiply, and divide smoothly. For a polynomial to be reducible over a specific field, its smaller factors must only use numbers from that exact field. For example, the polynomial x squared minus 2 can be factored if we use real numbers, because the square root of 2 is a valid real number. But if we are restricted to rational numbers or fractions, we are stuck. It becomes irreducible. The field dictates the rules of the game. This brings us to the most fundamental diagnostic tool, the root test for polynomials of degree 2 or 3. The rule states that a polynomial of degree 2 or 3 is reducible over a field f if and only if it has a root in that field. Conceptually, this turns the hard problem of factoring into the much easier problem of just looking for a single root. A root is simply a number that makes the entire polynomial equal to 0. If you find a root, it is reducible. If there are absolutely no roots in your field, it is irreducible. Remember, this specific test only works for degrees 2 and 3. Before we prove why this test works, let us see it in action with a concrete example. We want to determine if the polynomial x squared plus 1 is reducible over the field of real numbers. Since the highest power is 2, we are perfectly safe to use our root test. Our strategy is simple. Set the polynomial equal to 0 and solve for x. If the resulting values are real numbers, we have found our roots and it is reducible. We start by setting x squared plus 1 equal to 0. Subtracting 1 from both sides gives us x squared equals negative 1. Continuing our solution, we now need to find a number that when multiplied by itself equals negative 1. We take the square root of both sides. The square root of negative 1 is the imaginary unit I. This means our roots are I and negative I. Neither of these are real numbers. They belong to the complex number system. Because we could not find any roots within our allowed field of real numbers, our test gives us a definitive answer. The polynomial x squared plus 1 cannot be factored using real numbers, meaning it is strictly irreducible over the reals. Let us look at a slightly more abstract but very common scenario, testing over a finite field. We want to test if the polynomial x cubed plus x plus 1 is reducible over the field z2. Z2 is a clock math system that contains only two numbers, 0 and 1. Since our polynomial has a degree of 3, the root test is still valid. Because our field is so small, our approach is incredibly simple. We just plug both 0 and 1 into the polynomial. First, we substitute x equals 0 to check if it is a root. Evaluating at 0 gives us 1, which is not 0. So 0 is not a root. Next, we test the only other number in our field, which is 1. Plugging in 1 gives us 1 plus 1 plus 1, which equals 3 in normal arithmetic. However, we are working in Z2, where we divide by 2 and only keep the remainder. 3 divided by 2 leaves a remainder of 1. So the result is also not 0. We have tested every single number in the field and none are roots. Therefore, we can confidently conclude this polynomial is irreducible over Z2. Now that we have used this formula successfully, let us understand exactly why it works. We will prove that if a degree 2 or 3 polynomial is reducible, it must have a root. We start by assuming our polynomial f of x is indeed reducible. By definition, this means it can be factored into two smaller polynomials, which we will call g of x and h of x. A key property of polynomials is that when you multiply them, their highest powers add together. Because our original degree is exactly 2 or 3 and we are breaking it into smaller valid pieces, neither piece can be just a plain number with degree 0. They must contain the variable. Continuing our logical deduction, think about the numbers 2 and 3. If you split either of these into two positive whole numbers, at least one of those numbers absolutely must be 1. This means at least one of our factors, let us say g of x, must be a linear polynomial of degree 1. We can write this linear factor as a times x plus b, where a and b are numbers from our field and a is not 0. Now, because g of x is a direct factor of our original polynomial, any value of x that makes g equal to 0 will also make the whole polynomial 0. So we set our linear factor to 0 to find its root. To find this root, we simply solve the linear equation for x, which gives us negative b divided by a. Here is where the properties of a field become absolutely crucial to our proof. Because a and b are in our field and a field guarantees we can divide numbers without leaving the system, the fraction negative b over a is guaranteed to be a valid number inside our field. Plugging this value back in makes the original polynomial evaluate to 0. We have just mathematically proven our test. If a degree 2 or 3 polynomial can be factored, it is absolutely guaranteed to have a root in that field. This completes our derivation. So, we have proven that the root test holds. This brings us to a visual summary of our decision process. Look at this flowchart. When you are handed a polynomial, your very first check is its degree. If the degree is 2 or 3, you follow the yes path to the root test. If you find a root, it is reducible. If you do not, it is irreducible. It is a perfect closed logical loop. But notice what happens if the degree is 4 or higher. The root test becomes inconclusive and we must rely on more advanced mathematical tools. This flowchart we just saw leads us to an important limitation. It is crucial to remember that the root test only works perfectly for polynomials of degree 2 or 3. If a polynomial has a degree of 4 or higher, it might be reducible even if it has absolutely no roots. For example, the polynomial x to the 4th plus 2x squared plus 1 has no real roots, but it easily factors into x squared plus 1 times x squared plus 1. Because it can be factored, it is reducible. For these higher degrees, mathematicians rely on advanced tools like Gauss's lemma, which bridges the gap between integer and rational polynomials. You might be wondering why we care so much about breaking down polynomials. Understanding reducibility tests is absolutely vital in the real world, particularly in cryptography and coding theory. In modern digital security, such as the encryption that protects your bank details online, we rely heavily on finite fields and irreducible polynomials. In these systems, an irreducible polynomial acts just like a prime number to generate secure cryptographic keys. If a hacker can easily factor or reduce the polynomial used in an algorithm, they can break the code and steal the data. Testing for irreducibility keeps digital communication safe. We have covered a lot of ground today. Let us summarize the most important ideas. First, reducibility is simply about whether a polynomial can be factored into smaller, valid pieces. Second, the rules of the game are dictated by the field. A polynomial might be reducible in one number system, but irreducible in another. Third, for simple polynomials of degree 2 or 3, finding a root is the ultimate proof of reducibility. Mastering these tests allows you to break down complex algebraic structures into their most fundamental, unbreakable building blocks. Thank you for joining this lecture.